In this video, we're going to practice linear programming. So we're really putting two sections together. Section 2.1 is called a linear programming problem, and section 2.2, fundamental theorem. I find it's more efficient just to cover both of these together. Let's talk about what our goal is. We're trying to maximize or minimize a quantity with some restrictions. So for example, a company may wish to maximize their profit if they have limited amount of raw materials to work with. So let's jump into our first example. Each day, a company has 60 kilograms of wood and 100 kilograms of metal available. A chair uses a certain amount of wood, certain amount of metal, and yields a $14 profit. A table also uses a different amount of wood, different amount of metal, and yields a $20 profit. How many chairs and tables maximize the daily profit? So we're going to go through an 8-step process for solving this kind of problem. Most of the steps will be quite short, and everything will build on the topics that we've seen before. So step 1 is going to be called variables. And you can usually figure out what your variables are going to be just by looking back right at the end of the problem. The question was, how many chairs and tables maximize the daily profit? So our variables are going to be the number of chairs and the number of tables. So specifically, we'll let X be the number of chairs produced each day, and we'll let Y be the number of tables produced each day. And those are going to be our variables for the problem. From there, we're going to try to pull the information out of the question and organize it into a chart. So we'd like to see our variables sitting across the top of this chart. I'm just going to put those in brackets here. X represents the number of chairs produced each day. Y is the number of tables. So let's have chairs and tables across the top. And we also have some restrictions on how much of each material the company has available. So that's what we're going to see across the top of the chart. And then down the side, we're going to see our different restrictions. So we've got a restriction on how much wood is available, how much metal, and we also have some information about how much profit comes with these chairs and tables. So if we wanted to put units on here, wood is going to be measured in kilograms, so is metal. Profit will be measured in dollars. Okay, and our goal is to pull the information out of the question and just put as many numbers into these positions as possible. So let's take a look back at our question. First thing we're told is how much of these different materials the company has available. So we got 60 kilograms of wood and 100 kilograms of metal available each day. So that's 60 and 100. And there's not going to be a number in this position. Essentially, this position here represents what we're trying to find. We're trying to figure out how to maximize the profit. So sort of the point of the question is to figure out what's the biggest number that we could put here. So we'll just ignore that position for now. And then we'll fill in the column for chair and the column for table just by looking back at the question. Okay, so a chair uses 2 kilograms of wood, 4 kilograms of metal, and yields a profit of $14. So if we fill those numbers in, 2, 4, 14, like that, and we can do the same thing for tables. So for tables, each table, 3 kilograms of wood, 4 kilograms of metal, and a $20 profit. So there's our completed chart, and I would say main tip in terms of completing the chart, try to get your variables across the top. And if you can start with that, then that will lead you to an effective chart. So based on this chart, we're going to try to come up with some inequalities. And if we sort of fast forward through the problem a little bit here, we're going to try to get some inequalities, and then we're going to graph those inequalities. And that graph is going to lead us to a visual way of finding the solution. That's sort of the point of what we're doing here. So let's talk inequalities. Well, there's going to be an inequality coming from the amount of wood that's available. So let's think about how to build that. So each chair takes 2 kilograms of wood, and the number of chairs that we're producing each day is called X. So the number of kilograms of wood that we're using up just from chairs is 2X. If we do the same kind of reasoning for tables, well, each table takes 3 kilograms of wood. If we're producing Y tables, we have to multiply 3 times Y. So that gives us the amount of wood that's taken up by tables. And if we add those together, that's how much wood the company is going to be using each day. So I'm just going to write down some of the things I said here. So this 2 is kilograms per chair. The X is the number of chairs. So if you multiply these together, what you get is a number of kilograms just coming from chairs. And in a similar way, this is the number of kilograms just coming from tables. So if you add them together, you have the total number of kilograms that the company is using each day. Okay, now we know that they have 60 kilograms available each day. So we're going to put the 60 over here. And the idea is that we're going to have an inequality coming up. So let's just think about which way the inequality should go. It should go this way. So if the number over here is smaller, that's okay. If they actually use, say, 59 kilograms of wood and they've got 60 available, that's fine. So 60 should be the bigger number. You definitely would not want your inequality going the other way. See, if you had it going this way, then you'd be saying, oh, it's fine if they use up, say, 61 kilograms of wood in a day. And that's not fine. They would run out of wood at that point. So your inequality has to go that way. And let's now think about a fast way to build that inequality. So you can see that we've got our variables across the top here. So when I read the inequality, I just go 2 times x plus 3 times y, and then the number on the right side of the inequality is going to be 60. So let's try that for metal. Okay, so if we do it the fast way, we're taking the 4 multiplying it by x, we're taking the 4 multiplying it by y and adding those together. So 4x plus 4y. Our number is the 100, and then we just need to think about which way the inequality goes. So 100 is the maximum that the company has available in a day. Therefore, the inequality should be going this way. This is the number that the amount of metal that they actually use in a day. If that's 99 kilograms, that's fine, but would not be fine if they used 101 kilograms. All right, so those are our inequalities, and then there are a couple of other sneaky ones that we need to think about. When we're talking about physical objects, there's always a non-negativity condition. So you need your number of chairs to not be negative. So it needs to be, x needs to be greater than or equal to 0, and similarly y needs to be greater than or equal to 0. And that just comes from the fact that chairs and tables are physical objects. So in math, sure, we can have negative numbers, but in the real world, can't have a negative number of chairs or tables. So those are all our inequalities. And what we're going to be able to do now in our next step is graph these inequalities. So let's graph our feasible set, and this is going to build on some of the ideas that we saw in chapter 1. So let's make a graph here where we go maybe 30 units in the x and y directions. If that's not enough, we can always add more. And let's start to graph our inequalities. So first I'll do this one. X being greater than or equal to 0 just means we're going right of the y-axis. Y greater than or equal to 0 means we're going above the x-axis. And then let's look at our inequality at the top here. So what we're going to do is turn that into a line. It's going to be 2x plus 3y equals 60. And we can find a couple of points on that line just by setting our variables equal to 0. So if we set x equal to 0, that forces y to be 20. And if we force y equals 0, that forces x to be 30. Okay, so 30 comma 0 is here, 0 comma 20 is there, and so we're getting a line that looks like that. Okay, now we just need to test any point. Let's say we test 0, 0 in this inequality here. That would be true, and so that tells us that our inequality is going towards the origin, so it's going sort of down and left. So that's the fast version of graphing the inequality, and let's do the same thing for the other line. So our other line, write the details over here. So 4x plus 4y equals 100. If we set our variables equal to 0 one at a time, we can get a couple points. So 0, 25, 25, 0. So let's try to plot those points on our graph here. So 0, 25 would be about there, and then 25, comma 0 would be about there. So you've got a second line that looks like that. And then if we look up at our inequality here and we just test any point that's not on that line, I would say test the point 0, 0. That would be true. So that tells us that our inequality is going, again, sort of down and left here because we want to include the origin in that region. Okay, so let's see if we can shade everything in here. So we need to stay to the right of the y-axis. We need to stay above the x-axis, and we need to stay sort of down and to the left of both of these lines. So you can see there's going to be some point here where the lines cross. And so what we're going to get is this four-sided feasible set. So step 5 is going to be to find all the vertices for the feasible set. Usually what happens is most of them are easy to find, and often there's one or two that requires a bit of algebra. Once we've got all the vertices, that's essentially the end of the long calculations, and then the problem becomes pretty quick to finish from there. Okay, so let's put some effort into finding the vertices. 3 of them we should be able to write down right away. So 1 is the origin, 0, 0. The other one was this point here. So this was the point 0, 20 coming from the first line that we drew. And this second one here came from the second line that we drew. That was the 25, 0. So one habit that I usually get into is I try to label the lines when I draw them. So the first line that we drew was the 2x plus 3y equals 60. The second one was the 4x plus 4y equal 100. That way it's just a little bit easier to pick out our points when we need them. So this point here is coming from the second line. That's the 25, 0. Okay, so 0, 20 and 25, 0 go on the list. And then we've got one vertex that's going to be, a little bit more work to find. So if something's going to require some work, usually what I'll do, I'll just give it a name, like let's say that's A. And let's go through all the details of how we actually find A. So what we know about A is that it lies on the two lines, 4x plus 4y equal 100 and 2x plus 3y equals 60. And remember in chapter 1, we did some practice with finding the intersection of two lines. So that's what we're going to be using here. So let's solve for y in both of our lines. For the line on the left here, it's 4y equals 100 minus 4x, and then we can divide by 4. So y is 25 minus x. Whereas from the second line, we could say 3y equals 60 minus 2x, and then divide by 3. So 20 minus 2/3 x. So there we go. We've solved for y from both of our lines. And then the way we did this in class was we said, let's set y equal to y. So 25 minus x equals 20 minus 2/3 x. And we'll just get all our numbers on one side, all our variables on the other side. So if we subtract 20 from both sides, we've got 5 over here. And at the same time, we could add x to both sides. We'll just multiply both sides by 3. So we got 15 equals x. Yay, so we found our x value. And then the idea is that you can plug back into either equation. Just pick any equation that looks friendly to you. I would say maybe this one here, and then we'll get our y value. So sub into y equals 25 minus x. That tells us y is 25 minus 15. In other words, y is 10. And so there we have our fourth vertex. So A is 15, 10. So in step 6, we're going to write down the objective function. Objective function is just a fancy way of saying the function that you're trying to maximize or minimize. So let's look back at our original problem. So the question was, how many chairs and tables maximize the daily profit? All right, that tells us what we're trying to do. We're trying to maximize profit. And now what we need is a little formula for what profit looks like. And we want this to be in terms of x and y. So the secret to figuring this out is to go back to the chart that we built a bit earlier in the question. So here is our chart. We've used the top two rows to create our inequality, but we haven't worked with the bottom row yet. So that's exactly what we're going to do now. We're going to figure out what's a little formula for profit. Well, each chair gives us $14 of profit, and the number of chairs that we have is X. So if we multiply 14 times X, we're getting the amount of profit just from the chairs. If we take the 20 times the Y, we're getting the amount of profit from tables. So if we add those together, we get our total profit. So it's 14 times X plus 20 times Y. 14 times X plus 20 times Y. So here's the key idea that linear programming revolves around. So important that we're going to call it the fundamental theorem. The maximum or minimum value of the objective function occurs at one of the vertices of the feasible set. So what that tells us is that the answer to the problem is going to lie at one of the corners of that graph that we just drew. So here's how we're going to finish the problem from there. In step 7, we're going to make a little table, and all it's going to do is just list our different vertices. And for each of the vertices, we're going to just calculate what our profit is at that vertex. So every vertex represents a combination of chairs and tables, and for each combination, we're going to just calculate this quantity 14x plus 20y. So let's scroll back to where we had our feasible set. Here it was. We wrote down our vertices. They were 0, 0, 0, 20, 25, 0, and then remember there was that fourth one that required a little bit of work, which was 15, 10. Okay, so let's write those down. So now we're going to plug into our profit function. Okay, so with these ordered pairs, this is your X value and that's your Y value. So for the first line, our profit is 14 times 0 plus 20 times 0. In other words, 0 profit. So that makes sense. If you make 0 chairs and 0 tables, 0 profit. Next vertex, the X value is 0 and the Y value is 20. So our profit is 14 times 0 plus 20 times 20. That's 400. So this is actually calculating our profit in dollars. This is like saying if you make 0 chairs but 20 tables in a day, you're going to have $400 of profit that day. Next line, X is 25 and Y is 0. So that's going to be 14 times 25 plus 20 times 0. So that works out to $350 of profit. And then finally, when X is 15 and Y is 10, we get 14 times 15 plus 20 times 10. And you can grab your calculator there. That works out to $410 of profit. So remember what we're trying to do here in this problem is maximize profit. So now the problem comes down to just looking at all these profit numbers and you're just choosing which one is the biggest. Oh, 410 is the biggest profit on this list. So that's the maximum profit that we can achieve each day. Remember, we know that the maximum or minimum occurs at one of the vertices. So it's enough just to look at the different vertices of your feasible set and calculate the profit for those vertices. And then biggest number on the list, that's your maximum. So we're going to do one short final step. We're really just summarizing our answer here to make sure we understood what these numbers represent. So the maximum profit is $410 per day. And it's also nice in the answer to just give a description of the X and Y value. So let's say this comes from making 15 chairs and 10 tables. So we've figured out our maximum profit, and we've also figured out the way to get that profit, which is by making exactly 15 chairs and 10 tables. And I want to just mention, in terms of assignments and tests, typically what I'll ask you to do is to do some of the steps for a given problem. You typically won't have to solve it from beginning to end. So the goal is just to be familiar with each of the 8 individual steps and to be able to do those comfortably. Here's our second problem. Astronauts have 2 foods, and for simplicity, we're just going to call those 2 foods A and B. Food A has a certain amount of protein, fat, and carbs per serving, and it weighs 0.4 kilograms per serving. Similarly, food B has a certain amount of protein, fat, and carbs per serving, and it weighs 0.3 kilograms per serving. Astronauts require at least a certain amount of protein, fat, and carbs per day, and we want to know how many servings of A and B will minimize the total mass per day. So presumably these astronauts are going into space, and we're trying to make all their equipment weigh as little as possible. So we know the first step is going to be to write down our variables, and typically the question is asked in the last sentence. So let's look at this. The question is, how many servings of A and B will minimize the total mass per day? So let's let X be the number of servings of food A per day, and Y is going to be the number of servings of food B per day. And from there, we're going to try to make a chart that pulls out all the information from the question. So remember in our previous problem, we said a good way to structure your chart is to think about having your variables across the top. X represents servings of food A, Y represents servings of food B, and then you're going to have your restrictions in the different rows. So remember the restrictions were things like protein, fat, carbs, and we were also told the mass of each serving of food. Okay, so protein, fat, and carbs, if you care about units, those are measured in grams, whereas the mass of the actual food pack itself was in kilograms. So let's start to fill in the numbers here. We'll see if we've got all the rows and columns that we need in our chart. So food A has, in terms of grams, it's got 40, 12, and then 50 grams of protein, fat, and carbs in that order. So 40, 12, 50, like that. And if we do the same thing for food B, 10, 15, and 20. Okay, let's go back to the problem and see what else we were told. Oh yeah, we were given the weights or the masses for these things. So each serving of food A, 0.4 kilograms. For food B, it's 0.3 kilograms. So let's put that into our chart. So 0.4 and 0.3. Okay, and let's see what else we were told in the question. We're told that astronauts require at least a certain amount of protein, fat, and carbs. Okay, so we're going to need to figure out where to put that in our chart. We're going to put that into a column. So we're going to say required. And it makes sense that that should go into a column because basically this is where our inequalities are going to come from. So you can imagine you're going to have an inequality just from reading this way. So the requirements were 120 grams of protein, 60 grams of fat per day, and it was 200 grams of carbs per day. Okay, now we don't know this number here. That's sort of the point of the problem, is to minimize the mass. So in all of these problems, you'll always see that you don't have a number in the bottom right-hand corner. Okay, so that's our chart. We know we're done our chart when we've just pulled all the numerical information out of the problem. So that's great. So step 3 is where we write down inequalities based on our chart. So if you remember from our previous problem, basically we're going to save the bottom row of the chart for later. Bottom row is going to help us create our objective function, but all the other rows are going to lead to inequalities. So we're going to have an inequality for protein, fat, and carbs. And let's just remember the fast way to build the inequalities. So food A has 40 grams of protein per serving, but the astronaut is going to be eating X servings of that food per day. So if you multiply those together, that's 40X. And that's just from food A. You've also got 10Y coming from food B. And then what the astronaut requires is 120 grams of protein per day. So let's figure out which way the inequality is facing. And it might help to just go back to the question. We were told that astronauts require at least that amount of protein. So think of this number here as being the amount of protein that the astronauts are actually going to have in a day. If they have 121 grams, that's fine. But if they have 119 grams, that is not cool. So the inequality has to go this way. The actual amount that they have has to be bigger than or equal to 120. So which way the inequality is facing is just going to depend on the specific problem. So you can compare this problem versus our previous one where the inequalities were facing in the other direction. So let's think of this inequality here as being our protein inequality, and let's see if we can build a similar inequality for fat and for carbs. So for fat, it would look like 12x plus 15y, and again, that has to be at least 60. 50x plus 20y has to be at least 200. So that's just making sure that the astronauts are getting plenty of protein, fat, and carbs per day. Then, because this is a real-world problem, we have a couple of other inequalities, which are that x and y cannot be negative. So you can't have -3 servings of food A per day, for example. So I'm just going to write here non-negative. Anytime you're solving a real-world problem involving physical objects, you're always going to have those restrictions on your variables. And based on that, we are done with our inequalities, and we're now going to try to do some graphing. So when I think about these linear programming problems, usually I think of step 4 and step 5 as being the really time-consuming ones. So we're going to spend time graphing the feasible set, and then we're going to spend time finding the vertices. Pretty much all the other steps are fairly quick to do, especially once you get some practice with these problems. So let's focus on making a nice graph here. So I'm just going to do some work for each line over on the side. We'll start with the line 40x plus 10y equals 120, and we'll do our trick of setting each of the variables equal to 0. So if we set x equal to 0, our equation becomes 10y equal 120. So that would force y to equal 12. And if we set y equal to 0, then we've got 40x equals 120. So x would be 3. All right, so that's our first line. Let's draw our axes here. So we're definitely going to need to go as far as 12 in the y direction. Let's just go up by increments of 2 there. For x, we don't really know. So again, let's just go over in increments of 2. We'll see how much space we actually need. And we can graph this first line. So 0, 12, and 3, 0 gives us our first line. And we learned from our previous problem, it is usually smart to label your line just right at the bottom of the line there. So there it is. And if we actually wanted to turn this into an inequality, let's look up at our inequality. Here it is. So test any point. Usually we just choose x equals 0, y equals 0, and decide if that makes your inequality true or false. Well, the inequality would be 0 is greater than or equal to 120. That's false. So we're going away from the origin. We're going this way. A couple of other inequalities that are fast to do. We know x has to be greater than or equal to 0, and we know y has to be greater than or equal to 0. Okay, so that's 3 of the inequalities done already, and we've got 2 more bigger ones to go. So let's deal with this guy next. We'll turn that into a line, 12x plus 15y equals 60, and let's get a couple points on that line. So if x is 0, y is 4, and if y is 0, we'd have 12x equals 60, so x is equal to 5. Okay, so I'm going through this algebra a bit quickly just because it builds on what we did in chapter 1. So let's plot those points. I might do this one in a different color. So 0, 4, and 5, 0 would look like that. Okay, so we're getting some sort of line that does this. And again, I'm going to label that line. That's 12x plus 15y equals 60. So we're going to need to know which line is which when we try to find our vertices. Let's make that into an inequality by just testing any point. So if we test x equals 0, y equal to 0, that would give us 0 is greater than or equal to 60. That's false. So we're going away from the origin again. Good, so let's do one more like that. Finish off our picture. So here is our last inequality, 50x plus 20y. greater than or equal to 200. So we'll turn that into a line. And let's find a couple of points on that line. So still the usual trick of let x equal 0, figure out what y is, and let y equal 0, figure out what x is. So if x is 0, our equation is 20y equals 200. So that would force y to be 10. And if y is 0, then our equation becomes 50x equals 200. So 4, 0. All right, so I think I'll draw this line here in the black pen. So 0, 10 would be there, and 4, 0 would be there. Okay, so we get this third line, which looks something like that. And let's label that guy down here. So 50x plus 20y equals 200. So very last thing we need to do is just figure out which way that inequality is going. Let's look back up at our inequality. We got it at the top of the screen here. Plug in, say 0, 0. That tells you 0 is greater than or equal to 200, which is false. So that means we are not going towards the origin. We are going away from the origin. So you can see all three of these lines were sort of going up and to the right of the line. So let's see if we can graph our feasible set. So I'm going to just shade in our region in red. So if I start sort of at the top left of the picture, we need to stay to the right of the y-axis. Then we're starting to hit the blue line. Okay, we need to stay above the blue line. Oh, now we've got lines crossing, so now we need to stay above the black line. Again, lines are crossing. Stay above the red line, and then stay above the x-axis. So what we've got is actually this infinite feasible set, but we know from our previous discussion, it's really the vertices that we're going to be interested in. So let's make sure to highlight those. So there's going to be one here, one there, one there, and one there. So we're only interested in the actual corners of our region. So this one here, for example, at 0, 10 is not actually a corner. So you can see, especially for this problem, it really pays to make a careful sketch, enough detail so that you can see which lines are meeting at which points. So now that we're done that, we're going to work towards finding our vertices. And I think I'll just highlight them just to add a little bit more detail to this picture. So we got 4 vertices. Seems like 2 of them we're just going to be able to read off the picture. So the highest one and the lowest one we can just read off the picture, but the inner 2 are going to require a little bit of work. So let's think about the ones that we can read off right away. The one at the top is 0, 12. That was just one of the intercepts of the blue line. And the one right at the bottom right here, that's 5, 0. That's one of the intercepts of the red line. So we can write those down right away. So there we go. And then maybe let's give some names to our other vertices. So these 2 mystery ones, we'll call them A and B, and we'll just figure out how to find those. So A is coming from the blue line and the black line intersecting. Okay, so I'm just going to refer to the equations by the number that's sitting on the right side. It's the 120 line and the 200 line intersecting. So let's write down those equations. So we'll do some algebra in a minute to find A, but right now I'm just sort of organizing all the information. So A comes from the 120 line and the 200 line. And then we've got this other vertex B, which if we look back at our picture, that is the black line and the red line. So that is, if we just refer to the numbers on the right side, it's the 200 line and the 60 line. So that's the 12x plus 15y equals 60, and the 50x plus 20y equals 200. Okay, so there we go. We have our work cut out for us, and we know how we're going to go about finding those 2 vertices. So at this point, we don't need to look back at our feasible set anymore. So for completeness, I'm going to go through all the algebra for point A and point B. And of course, you can feel free to skip through that if you feel like you're comfortable with that. It's really just in case you want extra practice with the algebra side of the problem. So what we're going to do is solve for y in each equation. We have 10y equals 120 minus 40x, and then we can divide through by 10. So y is 12 minus 4x for the first line. And for the second line, let's try the same thing. 20y is 200 minus 50x, and then divide through by 20. So y is 10 minus 2.5x. All right, so now we can say y equal y. So 12 minus 4x equals 10 minus 2.5x. Going to bring our numbers over to the left side. So let's subtract 10 from both sides. We'd have 2. And at the same time, let's add 4x to both sides. So 4x minus 2.5x is what we've got on the right side. Okay, so then if we ask how many x's do we have? Well, 4 minus 2.5 is 1.5. So 2 equals 1.5x. All right, let's multiply both sides by 2 just to clear the fraction. So 4 is equal to 3x. In other words, x is equal to 4 over 3. So now let's plug back into either equation, whichever one we think will be easier to work with, and we'll get our y value. So looking back over our previous work, you can choose any of the equations over here or any of the equations over here. I think I pick this one. Doesn't matter which one you pick. So sub that in to y equal 12 minus 4x. Y is going to be 12 minus 4 times 4 over 3. Okay, so let's put stuff over 3. It's 36 over 3 minus 16 over 3 is 20 over 3. So there's our vertex A, 4/3, comma, 20/3. So let's go through the same kind of algebra for vertex B. So we're going to solve for y from both of the equations. Let's go 15y equals 60 minus 12x, and then we're going to divide by 15. Okay, so 60 divided by 15 is 4, and then we have this minus 12 over 15 times x. Okay, now just in the interest of keeping these numbers small, 12 over 15 can be reduced because the top and the bottom are both divisible by 3, so I'm going to make that 4 over 5. Just to make things a little simpler. So that's our first equation. And then working with the second one, 20y equals 200 minus 50x. Let's divide through by 20. So y is 10 minus 2.5x. I go y equal y. 4 minus 4/5 x is equal to 10 minus 2.5x. So now let's take that x value and figure out the y value that goes with that. So you can go back to any of these equations that you had written down earlier. I say this one looks relatively friendly. So we're going to take this x value and we're going to plug it into y equals 10 minus 2.5x. Okay, so y equals 10 minus 2.5 times 60 over 17. I can see that everything's going to be over 17. So let's take that 10 and multiply top and bottom by 17. Be 170 over 17 minus, now this number is just going to multiply with the numerator of the fraction. So that's going to give us 150 over 17. And there we have our y value. It's going to be 20 over 17. So wow, that was quite a bit of practice with fractions. Our coordinates for our vertex here, 60 over 17 and 20 over 17. So that is vertex B. So step 6 is going to be to write down our objective function, and we can do that by looking back at our chart. So here was our chart, and we said that bottom row is where the objective function is going to come from. So what we're trying to do is minimize the mass. If we think about what the mass is going to look like, it's going to be 0.4 times x. plus 0.3 times y. Because the idea is it's 0.4 kilograms for each serving of food A, and then you've got X servings of food A. So if you multiply those together, you got the number of kilograms just from food A, and then you add that to the kilograms from food B. Okay, so let's write that down. We are trying to minimize the mass, which is 0.4x plus 0.3y. So then last two steps. Step 7, we're going to make a little table, and then step 8, we're going to write down our answer. So we're really in the home stretch now after all that work with finding the vertices. So for the table, we're going to write out the 4 different vertices that we found. And for each one of those, we're just going to calculate this mass function, the 0.4x plus 0.3y. And decimals will be fine here, so we don't need to do any more crazy work with fractions. So let's summarize our vertices. We had 0, 12, and 5, 0 as the first two that we could find sort of automatically. For vertex A, we found 4 over 3, 20 over 3. Last vertex, which was quite a bit of work, was 60 over 17, 20 over 17. Okay, so let's try plugging in. I'll just show you maybe one example here of how we plug in. Let's look at this row here. So we're going to go 0.4 times the x value plus 0.3 times the y value, and just plug that into your calculator and just round off to a few decimal places. So that one comes out to 2.53. And if you do the other numbers similarly, you get 3.6 and then 2 exactly. And then the last one comes out to 1.76. So what we're measuring here, the mass of all this food product that an astronaut is going to consume in a day. So let's remember what we're trying to do. We're trying to minimize this mass. So we're just going to look at all these different values and we're going to choose the smallest number on the list. So that's this guy. So that is our minimum mass. So we can see why we had to put so much work into finding that vertex. And now we can give our answer. So let's say the minimum mass is 1.76 kilograms. And then it's good to say where that's coming from. So that's coming from 60 over 17 servings of food A and 20 over 17 servings of food B. So because these are food packs, we're presuming that they might be resealable, so it's fine for astronauts to have a fraction of a serving each day. If that were not the case, then in the real world, what you would do is you would just round your vertices to the nearest integer value, and then you would do some analysis based on that. But that's outside the scope of our course, so we won't worry about that. We'll just assume that they can have portions of the food pack. So we saw how to solve linear programming problems by graphing inequalities, and we did a bunch of algebra practice along the way. Thanks for watching.